In today's Bias Tech Threads podcast, where we discuss trends, challenges, and disruptions that are driving the AI-driven transformation, we have a sage panel of technologists and architects who are recognized names in the compute, system architecture, network on chip, and interconnect standards industry. And we dived into the exact topics that were front and center at Nvidia's GTC conference on March 16th. I might have to apologize that this podcast has been done on the road, so I apologize in advance for any hiccups that you might see during the recording.
Welcome to Tech Threads, Weaving the Intelligent Future, the podcast exploring the fast-paced world of technology. In each episode, we dive into the latest innovations in data movement, AI acceleration, and the transformative potential of chiplet technology. Join us as we explore the breakthroughs that shape the future of computing and hear from industry experts on what's coming next in the tech landscape.
Hello, and welcome to Bias Tech Threads podcast, where we discuss trends, challenges, and disruptions that drive the AI-driven transformation. Today, we have a very august panel of technologists and architects who have built their careers around and are recognized names in compute, system architecture, network on chip, and interconnect standards. They've led in their respective roles at companies like Intel, ARM, Arteris, Altera, Texas Instruments, and more. They also happen to be technical advisors to Bayer. So today we will talk to them about the exact topics that took top billing at Nvidia's GTC conference week of March 16th. Ty Garibay, our first guest, is the president and founder of Condor Computing. Previously, Ty was the VP of engineering at Mythic, CTO at Arteris IP, and he led worldwide IC design teams at Altera and TI. In days long past, Ty participated in the development of microprocessors at ARM, MIPS, Motorola, Cyrix, and Alchemy. He has more than 40 US patents granted. Our second guest, Dr. Phanindra Manua, retired in March 2025 after a very distinguished 4-decade career encompassing all aspects of high-performance computing architectures in both industry and academia. Widely regarded as an expert in coherent on-chip and off-chip protocols and interfaces, Phanindra led the specification and development of major coherent interface protocols, including AMBA5 Chai, Intel QPI, and some pre-QPI protocols included. Phanindra also spearheaded the design implementation of various memory path aspects in both ARM and Intel processors. Last but not least, Kurt Schuler is a semiconductor industry executive with more than 25 years of experience in leading product, technology, and business teams. He previously served as vice president of marketing at Arteris IP, where he grew the company into the industry leader of network on chip IP in automotive and AI and mobile SoCs, culminating in a successful IPO. Welcome, guys.
Thank you, Nando.
Thank you. So this should be an exciting discussion. To kick off, let's worry about the next big bottleneck. As AI models scale across hundreds of thousands of GPUs, moving data across racks, across clusters, and memory, and replacing pure computation in the middle, which is actually limiting performance. You're seeing the industry build photonics, high-speed data movement, all in there to kind of address that issue. And I think let's kick off as to where Jensen Huang mentioned at GTC, really that he doesn't see compute being the primary bottleneck anymore. It is really data. And to be fair to NVIDIA, they have actually invested in this, first with NVLink, then with NVLink Fusion, and consistent movement across it. So, Ty, since you're kind of leading the compute at this point, how about you kick off and talk about traditional compute and processing systems versus where we're going now?
You're right. Yeah, thank you very much, Nanda. I think it's a good place to start the discussion. One of the things that we've seen over the last 5 years is as AI has come to dominate, we once again have a workload that can drive the entire system design from the supercomputer down to the every single chip. This really hasn't been the case for decades, since scientific computing in the 80s perhaps drove computing. In between these times, we were really meeting general purpose computing requirements, which are very different. So now we have a driving customer that wants to see one thing: lots of computes with lots of data. And I think the other thing I wanted to highlight from Jensen's discussion yesterday was that Nvidia formally recognized that a diversity, heterogeneous computing is their chosen path forward now. So they have come out and said, we are going to have a combination of GPU, CPU, and inference engine from Grok. And then we're going to hook those up with lots of memory, both SRAM and DRAM, using proprietary and industry standard interconnect standards. So, that is a huge step forward for the industry, away from the GPU is the only thing you need and we will hook it up for you. So I think that sets a great leap-off point for the rest of the industry to now build on and say, yep, we agree, and here's our solution that is either complementary or competitive with the NVIDIA's offering.
Yeah, and so I think that is also a kind of a jumping off point, I'd say, to Phanindra, because I know we got that 15 years ago. We kind of pushed on coherent computing to scale at the as ARM started moving into this. Now you can actually see heterogeneous processing going through as well. So if you could kind of shed some light on what you've seen over the last 15 years or so, we'll not go back 4 decades, and especially the transition now and how fast it's going. How do you see that coming?
I mean, the heterogeneous computing itself is nothing new. It has been around for a long time. But what's driving, as Ty was saying, what's driving the new urgency in solving the data movement problem is more of a speed up of the compute systems, then the size of the compute systems, and the heterogeneity of the systems. Earlier, the sharing of the memory used to be software managed coherency, and that used to be sufficient for the speeds or to satisfy the compute engines. But with the disparity in the communication latencies and the compute performance growth and all, the need is to make the data movement more efficient, and the coherency a lot more efficient than what is software managed coherency can provide. So in the 15 years or so, the realization has come that hardware coherency is important and is the only way to go to get away. And for that reason, quite a few, if I may talk about standards and all, quite a few companies got together and multiple times, not once, try to come up with new standards for coherent interface designs and all, to share them. And one other thing that has created this issue, this urgency in my mind, is the number of players. In the old days, there used to be 1 or 2 main key players, Intel and IBM and somebody else, and everybody else used to follow them. So there's no question of having marketplace, so-called marketplace availability of chips that you can buy and hook up to whatever you want. Lately, I think that so many players in the field that you want interoperability. And for that reason, I think standards and solving the data movement problem is critical if we want to continue on the pace.
Yeah, thanks, Phanindra. So taking it from this, it might be useful to reframe it into different layers of computing, right? So Jensen last week also all talked about all 3. And if we think about scale out, which is effectively a kilometer or a meter problem where you're seeing computation across different data centers even, then coming down to actually a scale-up situation, which is at a meter level where you have number of components that are connected up in the same rack. We get down further into where Baya is more closer to working with, which is like the centimeter problem, which is within boards, because now you have multiple chiplets or chips working through a common board. But really, Baya's focus so far has been on the scale within, which is the on-chip fabrics or ability to make multiple chiplets happen in a package very efficiently. That's where a large part of the data movement problem is moving to because of the speeds and feeds that are needed. So Kurt, you've been associated with this for like 2 decades now. Could you take us through how you're seeing this transformation actually accelerating now versus what you saw, well, let's say a decade ago?
Well, when I was looking at this, working on the slides for this 15 years ago, saying, yeah, we're going to have this, all these different heterogeneous architectures, and, we're going to be able to take chiplets from different vendors and put them together and do all kinds of cool things. I was actually wrong. The real leaders of this ended up being a lot of the system guys. They don't promote it a lot as far as what they do, but I'm talking, you look on LinkedIn, you look at who Google has hired, who Meta has hired, who Microsoft has hired, who Amazon has hired. They're doing their own chips. What they're doing is they're owning all the different IP. And part of the benefit of that is that they can either make their own interconnect or configure their licensed interconnect, the best for their possible, for their use cases that they expect. Usually these chips are very, they don't do everything. They do a very particular thing very, very, very well. And so I think learning from them and what they're doing would give us a better idea of like what architectures work best for what are the best ways to communicate across chip. And we could talk about chiplets and the interfaces and, whether you do things at the protocol level or the flit level or the signal level, there's all kinds of trade-offs there. The only bad thing about that is these superscalers who, in a way, are kind of leading this revolution, at the chip level. They're not real open about their architectures, intentionally so. But if I had one wish, it would be to look inside and see what those guys are doing.
Well, let's take that kind of wish and convert that into, again, what problems are we trying to solve, right? So if, again, I'll take you into this discussion as a second question on that. Again, you've seen the interconnect evolve, as has Phanindra, right? What are the challenges with the traditional approach that are being exacerbated at the moment? So it's not that data movement has not been a problem before, right? Right now, it seems to be scaling much, much faster, right? Exponentially. So can you kind of highlight what are the kinds of problems? And then we'll probably throw it back to Phanindra after that to look at how would standards try to help it, what kinds of standards. But let me start with you, Kurt.
Okay, well, I think it's a big problem. You're dealing with like scale, and then you're dealing with abstraction, right? And as you get larger and larger systems, maybe spanning different chips, you've got to abstract up to be able to understand that, be able to implement an interconnect for that. Now, when you start abstracting things up, you got to have a really smart way to make sure that you're dealing with the details really, really, really well. Because that's what's going to catch you, if you're doing coherence and sync across, long pass and die, you got to deal with that, QoS, all kinds of different things there. But, I think in the future, the interconnects that you're able to describe at a higher level and quickly be able to get that into a verifiable solution as quickly as possible, That's going to be the key. If you're individually placing blocks and bits around, it's just not going to work.
Got it. And if you think about this, right, there's an abstraction level. There are certain challenges that you face, such as congestion on die, across die. You need to do arbitration across different types of workloads, and that gets more complex. When you're starting to put networks into place, the traditional tree or a standard mesh doesn't work. You have to start different topologies, right? And in order for you to understand what you're building versus what needs to be built, you need to know what kind of workloads are running for it, right? So I think you've kind of mentioned that those are the problems. I'd probably start also thinking about that from Funninder's standpoint. How do standards help with any of this? For example, how do you enjoy partitioning it? What can standards help with that? Can standards help with organizing data movement, arbitration, etc.? So, Funinder, you want to enlighten us on that?
Yes. Let's see. That's a huge question, actually.
Yeah,
sorry, I didn't mean to cause trouble, but this is exactly
you
what
can start with the dinosaurs and just get to today. A couple minutes.
And everybody always agrees during a standards meeting, for sure.
Yes, definitely, and they don't take too long to get resolved. So standards, as Kurt was pointing out, I mean, the heterogeneity is not only in the systems but also on a chip now, on a die. Earlier used to have a CPU die and I/O die and memory die and things like memory controller die and all. I mean, let's talk about many, many decades back. But now you have heterogeneity of multiple cores, compute engines, coherent compute engines, non-coherent compute engines, not one or two, up to 192 coherent compute engines in an ARM or a AMD CPU, along with I/O processors, DMA processors, PCIe root complexes, and so on and on. So the heterogeneity is all the way down there. So somebody like an open system or open architecture like ARM, they would like to share their architecture with everybody else and contribute to the society and the community and enable them to build their own systems using ARM architecture. So for that reason, ARM came up with the AMBA, as everybody knows, AMBA specifications. Standards. And so the standards can be on-chip standards or off-chip standards. And the coherent ones, of course, latest in the last 15 years has been the CHI coherent standards, which is used very widely and is non-confidential. Anybody can download it and contribute to it if they want to, talk to ARM folks and contribute to it. So it's semi-open. And that makes, beyond that, if we jump into die to die and chip to chip, we have, a decade back, started C6, which was supposed to be a coherent interface standard. And why I already mentioned why we would like to go to a coherent interfaces instead of using PCIe or Ethernet or any of the older technologies, communication technologies that were already there. For the shared memory reasons and fast movement of data and non-movement of data, actually. Efficient movement of data doesn't include that you must move the data. So for that, you can do caching at different levels, and find out if the memory is not cached or the line is not cached, then you don't even have to get it from somewhere else. You can get it from memory or work on your own copy and things like that. So standards are required so that you can plug into or you can develop compatible, interoperable chips that work with the rest of the community. And ARM has been very good at that. in my experience. And of course,
I think.
Yep, go ahead.
No, go ahead. Finish your thoughts. Sorry.
So I was just going to say that just to complete the C6 and chip to chip. So looking at C6, after that, Intel, etc., others came up with CXL, open standard for chip to chip communication interface standards. And of course, then UAL is something new from AMD and their colleagues. NVLink Fusion is not a fully open, but is a result of all of these others. Everybody is seeing the need and to get a foothold ahead of everybody else. So that, but underlying all of them, of course, is AMBA CHI, I would say. And you don't have to be an expert in the internal coherence protocol, as long as you can interface to it and let somebody else like Baya or somebody build the interface chips, build the communication program, the underlying fabric and communication protocol, which Baya is. That's the goal of Baya, and Baya is doing a very excellent job of that, I think.
Thanks, Faridar. I think what you point out is quite relevant in that we can't grow an ecosystem and increase the radius of innovation, shall we say, without standards. But standards also have a way of slowing things down. Some for the good, some for the bad, just because getting agreement across, right? So, in fact, NVLink's potential success is because it was almost proprietary and they could move a lot faster. And they kind of licensed it out based on them. What UA and the Fusion is kind of a step to kind of scale it out. UA Link is more of a consortium trying to build it, and we'll see. There are some natural things that slow down a consortium versus a proprietary standard, but there's also the benefit that comes thereafter, right? So obviously what Intel did with PCIe, and then of course the UCI standard that came out after that, has helped grow the communication and interoperability between chips. If I were to kind of take that now to a consumer of standards, let's say, I'll put that hat on you, Ty, right? You've kind of looked at being on both sides of that coin, but if you were to kind of pick what are the standards that you feel are going to be critical going forward, you've had the processing side, you've done the AI side with Mythic and others, you've done the FPGA side, which is kind of an interim between them. How would you take in from today's list of standards? Where do you see that going and helping the industry scale?
It's a really interesting pivotal time right now. Nvidia did a great job of kind of listing out how we got here and where we are. The interesting I hark back to Kurt's comment of having started interoperability 15 years ago, bright-eyed, bushy-tailed, and believing in the mission, and then realizing that we were probably a decade or two early together. And the proprietaries, the big system houses like Nvidia has become, but Amazon, Meta, Microsoft were able to continue that push internally that we tried to start as either silicon vendors or IP vendors in that time frame. And so the work continued, but it didn't resurface until more recently, now that we've gotten to the point of those big superscalers needing or wanting to take advantage of chips and designs from outside. As long as they were able to meet all of their own needs, they didn't really need to worry about sharing or being open or being able to be interoperable. So now, as we move forward from here, we have, we said NVLink, said UAL. I think we have to include CHI chip to chip as an underlying protocol as well, although it's not clear how much traction it's got yet. And all of those implement some form of off-chip silicon protocol that rides usually on top of SerDes, but could also be implemented with bundles of wires type physical transport. I guess the challenging part at a system level is now putting chiplets or chips together using these interfaces. But within the chip, most of the transactions are going to be CHI. And you're going to take CHI up to the interface block, have that interface block do the transforms to communicate to the next chip, and then on the other side of the transfer, it'll be turned back into CHI. So for most IP vendors within the community, it is sufficient to get to a CHI level and then allow the interconnect IP vendors to do the transactions from there. I think what the opportunity is for interconnect then is to say, my job is not only to make a network on chip work, but a network across chips, network across chiplets, a network across packages that can scale both from a purely technical point of view. In other words, it'll function, but that will also perform. And that is the real challenge, that if we can enable many customers to do that, it can open the playing field for more and more participants to deliver very high quality solutions based on proprietary approaches.
I think that makes a lot of sense, right? So if you look at the AMBA standards, have been more than sufficient for on-die fabric. Now they're beginning to slowly go towards the chip-to-chip and the die-to-die standards as well. And it will naturally evolve. And then maybe some specific standards like NVLink Fusion or UA-Link or ESUN, etc., that are coming up for scale up and scale out, will also have, if you want to get the best out of it, integrate much closer to the die as well, right? But one of the things you said here kind of gives us a little bit of a segue into the understand of data flow, understand of performance, understand of really partitioning.
Nandan, before we go there, can I interject briefly?
Go ahead. Absolutely.
Ty was mentioning about CHI being ubiquitous and all that, and I agree in some sense, but one needs to be careful when they're reviewing or evaluating a protocol for their own purposes. They don't need to be implementing the whole thing, right? They can subset it, and some protocols subset very easily and some don't. And so let's say CHI, if you just need the non-coherent or the IO coherent part of it, you can always subset it. And that might be much, much simpler than, make your life much simpler than trying to understand and comprehend the total CHI spec, or any spec for that matter, not only CHI. So just wanted to caution people that are evaluating. So not to get scared about with looking at an 800-page specification.
I think what you mentioned is two things, right? One is the layering of this spec, and there are effectively references of what is good for what, right? So if it's IO coherency just to maintain for mainly data flow type or data path type of engines, then focus on that. Maybe there are references or standards to be set within that as well, which are a subset of the main standard. And I think that's happening, right? The other thing that I wanted to bring in is the standards also evolved for the thing that you most mentioned in the previous section, which was it's about data movement, but also not movement, right? So when you talk about caching, how can you make sure that the caching is done ahead of time, if you know where the data locality is, how do you partition it? The cache stashing ideas that were put into the standards, as well as into the interconnects that are building it. So I'll kind of take that question towards Kurt, because he had brought in the partitioning understanding of performance, which is where we're going right now. How do you see that evolving over the coming, let's say, year or two? Because when Bayer came into being, shall we say, 3 years ago, one of the key tenets was we want to make sure that people can design what they want to with the workloads that they want to do with. And so when they actually go to actually implement that, that becomes a design intent as opposed to design reaction, right? Yeah. So you want to talk through that, because you've lived some of that over the last decade, and you're seeing the changes going forward.
Yeah, I mean, if you look at, the start of my career was in servers at Intel, and, typical von Neumann architecture, and, we had this wonderful feature called, SMT, symmetric multi-threading, and then eventually got to true, multi-chip. But, you had a cache there, then you're going out to a memory controller, the on-chip RAM, and then from there, to a hard drive. Didn't really have SSDs much then. Nowadays, if you look at these architectures, it's like instead of having one big monolithic processor, as we were talking about, you might have smaller compute engines, and they might be focused on a subset of mathematical functions and data flow functions required for AI. Depending on what kind of LLM and CNN you're doing, things like that. So you're seeing architectures that have more and smaller processing elements. And then you talked about locality, data locality. For some of these things, especially when you're doing, gathering functions, things like that, you're going to have this memory really close, physically close on the chip for latency and bandwidth purposes to these different processing elements. So you end up with block diagrams that really don't look like anything that we've seen before in the past. So for the interconnect, it's really important to be able to handle these truly heterogeneous, non-mesh, funky-looking architectures. And one of the key things, I think, for anybody who's working on these things is you know mathematically what you need to do. You know what your data flow is going to be. But how do you simulate or infer what the performance of what you're going to do in your architecture is versus that? And I think that's a real big challenge for these guys.
Yeah. And if we kind of took that back into the performance realm, right? You've kind of done this across multiple of your both current and past implementations. If you look out a little bit and say, finally, if you think about compute engine, we used to focus on the processor, but now we're talking about 192 processor solutions. So you're talking about 264 process solutions. When it comes to AI acceleration, it's even longer, right, or larger numbers. So how do you see that now? As your as a president of quantum computing, let's say, has your mindset changed towards where the compute is now within the network, or do you still look at compute outwards?
Yeah. So in my day job, I still have to look at compute outwards. But as I look to how do we help our future customers build their solutions, it has to be a much more integrated approach. And the simulation of requirements are really continuing to be challenging. We have semi-infinite computes, but the problem is that those semi-infinite computes for simulation are trying to simulate semi-infinite computes for AI, and so the scope of the two is still a way out of whack. I think Kurt mentioned a while back that that it was necessary to think about levels of abstraction. And so, what we've been working on is, of course, we're creating IP within a level of abstraction that is very low within the CPU, but then trying to figure out how do we make that usable for customers in a system simulation, working with Bea or other maybe potential vendors to say, here's how our IP will behave in a system at a sufficiently accurate model to model data flow, to model time at a huge transfer level, much more than 4K elements at a time. How do you model sustained transfers so that you can model the streaming behavior of a data flow engine as a target? And so if we can provide levels of or an abstract model that can then fit into a system level model of the on-chip NOC, which can then be expanded to a multi-chip model of how multiple chiplets can work. That's again where I think our customers, our combined customers, are going to be. You're going to see value. They're going to be motivated to leverage that type of capability to say, that addresses my problem, not just your problem, and so. I think we can differentiate there in terms of the solutions we make available to our common customers. As we move forward, there needs to be some more thought in terms of abstraction to model even higher levels, and get back to, some of the, I'm sure that the big system houses still do this, but maybe make more available the stream level modeling that we used to do in the old days. And so, that's probably still another step forward for EDA companies and modeling companies going forward.
Got it. Yeah, and since you've kind of brought this up, right, and we've been having a pretty energetic discussion, I want to kind of move towards. I'll get back to your network compute discussion in a second, but I'd kind of push towards Anindra and ask about, like, if you're talking about the customers of SoCs or customers of systems. So I would say today, while the likes of Nvidia, AMD are strong, it's really the hyperscalers and the consumers who are delivering the AI services that are also taking matters into their own hands, right? So they're building the infrastructure for it, or it's not now, they've been doing it for a while. They're taking even more stronger view at it. So clearly, at a system level, right, you have to talk about efficiency, and people are talking about, picojoules per bit of compute. You're talking about throughput, picojoules per bit transferred. How do you see the infrastructure and hyperscalers kind of moving in the system direction, Anindra? Because obviously you've been in a lot of those discussions. A lot of your standards development did take into account what would be necessary. So you didn't have heavyweight, or you could lighten it as needed. You had to be thorough, but not. How do you see the hyperscalers moving and moving the industry in that regard?
Well, if you want to talk about the topology, I mean, there's aspects of topology and what compute to move into the network itself, or different levels of the network, the interface, the die interface, the chip interface, or a complete chip, separate chip. But you clustering of the functional components at the sub-chip level or sub-die level, and creating cluster controllers, which might be coherent managers, ordering managers, interface at the interface or within the chip, or like the Nvidia and all are trying to sell, or even CXL switches are taking some part of that responsibility of ordering and coherency management. And in addition to that, I mean, I see, at least from my experience, past experience, there's a lot of discussion on atomics, moving compute away from the compute engines towards the network, or farther away from the compute engines. It can be within the network at these controllers that I mentioned just now, at the interface of the chip, at the interface of the die, or a separate chip, or a memory controller, or any of those levels. That way, you don't have to move the data into the compute, near the compute, and do the processing and send it back again. I mean, that's one. But the bigger picture is that as mentioned earlier, that AI workloads have changed the data exchange or data sharing pattern completely. I mean, they're very well defined now, with 2 or 3 major ones like gather, scatter, or what is called broadcast, or a multicast. Do some operation and scatter them, or gather and do some operation and save, and things like that. So the major focus is to make the movement of data for those operations to be more efficient. The fabric needs to be a lot more amenable to reconfiguration based on the workload, reconfiguration based on the data movement requirements, the results of the modeling and all that results. So you cannot just say that this is it, this is what I'm going to give you an 8x8 mesh, and you only can connect a home agent here and a compute engine here, and that won't work anymore. It has to be a reconfigurable, readjustable in terms of throughput, bandwidth, width, everything, I mean.
Right. So I think you're kind of pointing out a few things here, right? So to me, that's very much on that. The topology needs to be movable. There should be a lot of flexibility, both while you're designing, right? Pre-silicon design, as well as a lot of reconfigurability and post-silicon tuning that may be required for future-proofing. Right? And things like multicasting are becoming almost checkboxes rather than special capabilities, especially within the fabric or the network. So I'll kind of point to Kurt and ask, you've kind of set the tone here, right? How would you say, especially things like in these heterogeneous systems with all these new capabilities, how are hyperscalers or automotive systems that are much more complex handling that, and what should they be doing differently?
Well, as we talked about, the processing elements are the functionality is fracturing into more and different types of processing elements. Mm-hmm. The memory required in the system, whether it's SRAM, caches, what have you, that is also fracturing and moving around throughout the architecture. If you kind of take it to an extreme, I remember, Ty and I, we had some people come from, I think it was the UC Santa Barbara, some experts there talking about, in-memory compute and what some of the ideas and capabilities and differences were behind, doing things that way, bringing the compute elements into the sea of RAM, if you will. And maybe in the future, we'll find a way to take advantage of that, kind of breaking down the process and elements into more and more finite things where they can be really close to, a larger core of memory and have a lot of them. But I don't know really what the state of the art of that is. I think Ty knows some about it. But
yeah, thanks, Kurt. Yeah. I think that's an interesting. I guess it's almost the antithesis of what we're talking about. It's the in terms of data communication, it's not communicating the data as part of as then declaring victory. In inference, AI inference today, I think we're seeing the eventual victory of SRAM, with Cerebras emerging as a viable company that will probably IPO, with Grok's architecture being adopted by Nvidia. There's several others in the industry that are doing variants on this. But those aren't exactly compute in memory, but they're compute very near memory. And architecture is designed to absolutely minimize the amount of energy and time used to move data around. And so those architectures, I believe, will probably win for inference, eventually driven all the way down to true compute in memory at a analog or optical scale that can achieve levels of compute and energy efficiency that really can't be competed with if you're moving data around as digital bits all the time. And that's the pure inference side. And then what NVIDIA has said is, okay, I need a agentic AI component, which is CPUs, and I still need training, which is still probably going to be GPUs, to be able to have a complete solution. So even though hopefully a lot of the most heavy usage driven by inference will eventually move towards lower data transfer requirements, there's still a huge amount of compute that has to do with CPUs and GPUs that we need to figure out how to connect, and then connect with these inference engines very efficiently across both the network, the full internet, but also inside the data centers. And so that's kind of the opportunity, is to be able to communicate with all of these different types of compute and make them all efficient, or as efficient as possible in this environment.
So yeah, thanks, Kurt, for moving the conversation there. I was going to ask Ty about this anyway, especially on the edge. I think both Ty and I have been associated with our past lives with inference engines that are taking alternate routes, whether it be event-based or in memory. And I think, Ty, your past work with Mythic also was effectively in that idea of being in-memory compute. So I think time flies when you're having fun. So we're pretty much at the end of our podcast here. And going from in-memory compute to network is the compute, I'd love for you guys to summarize your thoughts, probably in a very short description of what do you think network is the compute means to you guys. I'll start with Ty.
Oh, okay, thanks. So to me, network is compute is really just saying that we're going to have many, many different compute elements distributed at the edge, mid-range, and then in the data center, exactly like today's telecom infrastructure is built. You'll have phones, you'll have PBXs and boxes at towers, and then you'll have data centers handling calls and the backbone. And I think that's a model that we've proven works and maps onto the existing infrastructure of fiber in the world. So how we get data from one point to the other is the big network question. And then, but at each point where it's processed, it needs to be moved at a bit level to where it's going to be used. And that's where, we can make sure that we're being as efficient as possible and enabling each type of compute to be as efficient as possible.
Sure. Yeah, I think with all these heterogeneous data flows, I think eventually we're going to have to get, like in a big, huge computer network, you have a network operations center, right? And they're figuring out through computers, of course, hey, we got a huge bunch of trading volume going on right here because New York Stock Exchange is open. So we got to open this up and allow them to have, the lowest latency possible because our trading customers at this time of hour need that. And then later it's like, oh, everybody's at home watching TV. Okay, we got to open it up so the Netflix guys can, pump out their videos so that I can watch Ozark and become depressed about human nature. So, there is some control that I think will need to be added into these interconnects within these systems because there are different use cases. These things are not just homogeneously always, flowing with a nice stream of data that's easy to predict exactly what's going to happen. So I think the kind of network control and how you get a view within the system, however you define it within the chip, multiple chiplets, within the rack, larger than that, that will be an area where I think there's going to have to be some innovation because right now we haven't really dealt with it.
Cool. And Tanindra.
I think Ty and Kurt covered most of the stuff, but I would add that compute in the network is not only clustering, as I mentioned earlier, and trying to figure out where to put the cluster, what level of clustering you want to do, and that cluster controller being able to caching is also part of the network compute, and some of the atomic operations, filtering out operations from data movement from going any farther than strictly required. That kind of filtering and all has to move into a smart, I would call it a smart interconnect. Yeah. Just to not, I think, just to add to that, anytime a discussion happens any discussion on data movement and all, we naturally tend to talk about AI training workloads because that's the most exciting and most heavy. Mm-hmm. But I think the low-hanging fruit, as Ty pointed out, is the inference. Mm-hmm. Maybe, I won't say easier to solve, but simpler to solve than the training problem, but might not be people might not be paying attention to it, but it's, in my view, it's the bigger market for independent companies like Bias Systems. And not to forget that and not to complicate our lives, I think we should concentrate more on, or at least bring that into focus.
Understood. And so I think I would kind of capture that as it's still not one size fits all. So you have to customize your solutions to what they're trying to do. AI is about data and data movement and data compute. So if we think about any kind of computation, whether it's for inference or even some aspects of specialized computing, how the data moves, how the data do the computing is basically the network is where it is. The memories are integrated in the network. The compute is integrated in the network. So effectively, you're thinking about solving the whole problem rather than the widgets themselves, right? So effectively, the whole thing is a system that solves it. And to me, that's what network and compute is for us. And with that, I think I'll thank you all for a pretty stimulating discussion. Obviously, your insights are valuable on this podcast, but also as Baya continues forward. So again, thank you very much. And look forward to kind of what the future brings.
Thank you, Nandan.
Thank you.
Bye, Ty and Kurt.
Bye.
Bye, guys.
Thank you for listening to Tech Threads, Weaving the Intelligent Future podcast. Join us monthly for insights into the evolving tech landscape and the future of chiplet technology. If you enjoyed today's episode, don't forget to subscribe and share it with your network, and stay tuned for more expert discussions. Let's weave the intelligent future together.